So, hello everyone. My name is Emmanuel. I'm from Cornell. And as you have probably noticed, nowadays, voice interfaces are becoming more and more popular. Amazon Echo, Google Home, those are just some of the examples for devices that are primarily focused on voice-based interaction. And already nowadays, some of those devices give you simple access to data. For instance, if you ask about the Bitcoin price, then many of those smart speakers will answer with a highly simplistic description of the corresponding time series. And our goal is to significantly extend those voice query capabilities towards more complex queries and more detailed, precise descriptions. And by that, we hope to benefit mainstream users for whom voice-based access could be very convenient to get some high-level insights about a data set, but also we hope to benefit visually impaired users who cannot use traditional interfaces. Now, in order to enable voice querying, there's two challenges. The first challenge is to translate voice input into queries. The second challenge is to translate query results into voice output. And in this paper here, we're focusing on a second challenge, which we also call data vocalization. We focus generally on OLAP-style queries of this format here. So we are aggregating, and we are aggregating for a data subset, and we are breaking down aggregates by some number of dimension columns. The result to such a query is a table which contains aggregate values for combinations of dimension values, and in general we assume those results are too large to read them out row by row to users. So instead, we want to rather focus on describing the most important high-level trends and tendencies in those query results. Let's make things more concrete. Now consider this result here, for instance, from a query which asks about flight cancellation probabilities broken down by season and by region. And that is one out of several queries which we will use in our experimental evaluation. And as you can imagine, if I would now start reading out to you specific values for all of those fields, then that would become tedious very quickly, and nobody would be able to remember all of that anyway. So a better approach would be to say something like, the average flight cancellation probability is between 1% and 2%. Values increase by 50% for flights in the Northeast and by 100% for flights in winter. Now this gives you some of the high-level tendencies, some first impression of the data, and it is perhaps the best we can do within a reasonable speaking time, right? So in the following, I'm gonna demonstrate an approach to generate speeches of that format. We generally assume that speaking time is very precious. So we want to use it in the optimal fashion, and that motivates us to frame voice output generation as an optimization problem. Our goal is to maximize the precision of the description under constraints on speaking time. And at the same time, we adopt the holistic perspective on voice answer generation, which means that we do not separate between query processing and voice output generation. Because if the voice answer has to be very coarse-grained anyway, then spending processing time to generate the very precise query result is actually wasteful, and we will consider that in the following. We assume the following problem model. We're given an OLAP-style query as input, and processing that query on data yields a query result. Now our goal is to optimally summarize that query result by a concise speech description. And we also assume that we have a model about how users translate a speech description that they hear into their own mental model of the data. And I'm gonna go more into detail later about how that model looks like. Now, given this, we compare the mental model of the user after listening to the actual distribution of the data, and our goal is to minimize the distance between those two, given constraints on speaking time, and at the same time we want to minimize processing overheads in order to get there. That is the higher level problem. For the speech structure, we deliberately use a very simple grammar because that reduces the search space and thereby speeds up optimization. We start our speeches with a statement about the typical values in the query result, and then we follow that up by a series of refinement steps that refer to specific data subsets. For instance, this is pretty much the speech that I gave before. We start with a general statement about typical cancellation probabilities, and then we refine this for seasons and for regions. We want to find out how average users transform such speech descriptions into a mental model of the data. And to find that out, we performed several user studies in which we played speeches to users, and then we asked them questions about the data in order to find out what they intuitively assume. First of all, we verified, for instance, that most users tend to assume the most uniform distribution in the data that is consistent with what they hear in the speech. And that is an assumption that has been used already in prior work, but we wanted to verify it in practice and for voice output. Also, users tend to assume independence between different factors such as season and region, and in the absence of further information, they assume something which resembles a normal distribution with relatively low variance. So these are some of the things that we found out. You can find more details in the paper. And that means, for example, that if the user hears something like the average delay is 10 minutes, the user will typically translate this into something that resembles a normal distribution with that mean. Once we refine this by the region, then users will tend to imagine two different distributions, and once we refine that even more, we get 4 different distributions, and we will judge the quality of those speeches by how close that distribution comes to the actual data. And of course, that user model is simplifying, but we will show later that the quality estimates that we derive from it correlate quite well with actual user preferences. Now, a naive way to generate speeches of this format would be the following here. We execute 3 consecutive stages. First, we process the query, then we generate the speech, then we speak the speech, right? Now, this means that latency is proportional to query processing time and to speech generation time. But this is highly suboptimal because it doesn't consider the particularities of voice output. Because voice output is actually delivered incrementally over time. This means that the system does not need to know the last sentence of the speech while it is starting to speak out the first sentence. And we exploit this by essentially pipelining those 3 stages at a granularity of single sentences, thereby overlapping processing time and speaking time. So while the system is speaking out the current sentence, it performs further background processing in order to select the next sentence. And this means that we gain typically several tenths of seconds of processing time without increasing latency from the user's perspective. Now, the other thing about voice output is it has to be very coarse-grained in order not to overwhelm the listener. This means generating precise query results is actually wasteful, and instead we rather want to use sampling. We use a specialized sampling strategy in order to figure out optimal speech descriptions without ever actually generating the query result. So given data and a query on that data, we first of all build the search space for speech descriptions, represented as a tree, where each tree node is associated with 1 sentence. And you can form a speech by taking a path from the root node on the left-hand side to one of the leaf nodes on the right-hand side. And what helps us here is that speech descriptions have to be very short and also very coarse-grained, because that minimizes the size of the search space. And now we want to refine our quality estimates for different speech descriptions via sampling with a high frequency. So in each iteration, we take 1 small sample from the data, and then we use that small sample in order to predict the value in 1 randomly selected field of the query result. And then finally, we select 1 sample from our search space, and we use that query result field and our current estimate based on the data sample in order to refine our quality estimate for the speech candidate, right? So the fact that we take a sample from the data, a sample from the query result, and a sample from the search space means that we can iterate with a very high frequency. And those speech candidates to evaluate in each iteration, we don't select them randomly, of course, but rather we use an algorithm called the UCT algorithm from the area of reinforcement learning, which will optimally balance between selecting speech candidates that currently seem promising in order to refine their quality estimates, or selecting speech candidates about we know very little for the moment, so we want to get some first impression for their quality. An effect that we iterate with a high frequency, continuously refining our quality estimates, means that we can very well align processing and a speech output. Let's, for instance, assume that we are currently speaking out the sentence, the average delay is 1 minute. Then we will continue sampling in the background in order to refine our quality estimates. And once we reach the end of that sentence, then we'll simply change the route in our tree, starting from which we take samples to the next node that we select for speech output. Here that is the node values increased by 5% for flights in the Northeast. And in that way, we can even reuse the quality estimates which we have generated for the relevant subtree previously. All right, so that is our holistic approach for query processing and voice answer generation. We evaluated in experiments and compared against various baselines according to various metrics, such as, for instance, the latency, meaning the time between the query comes in and the voice output starts, or the quality of the generated speeches measured by our model, but we also performed user studies and evaluated, for instance, the accuracy at which users answer questions about data after listening to different speech descriptions, and we asked users directly for their preferences. Now, here, for instance, we compare the holistic processing against two baselines for different queries on a data set about flight cancellation probabilities. We compare according to the metrics latency and quality of the generated speeches according to our model. And we compare against two baselines. The first one generates guaranteed optimal speeches by first of all fully processing the query and then calculating the precise quality for each speech candidate in a search space. The second baseline uses the same sampling strategy that I have shown before, but it does not overlap speaking time with processing time. And as you see here, generating optimal speeches takes often prohibitive amounts of speaking time, several tenths of seconds sometimes even. On the other side, generating speeches via naive sampling results in speeches of a very bad quality. So it seems that the holistic processing strategy realizes a very attractive trade-off between those two metrics. It is very fast, and at the same time, the speeches it generates are nearly always the same ones as the optimal ones. And even in cases where that is not so, we generate speeches that are very similar to the optimal one. If you take, for instance, the query result that I have shown before, this is one of the few examples where the holistic approach generates a slightly suboptimal speech. Here are the speeches generated by those different approaches. And you see that, at least in terms of absolute values, the optimal holistic speech are very close. And also in terms of the tendencies that they consider most relevant, those two speeches are quite similar. On the other side, the speech generated by naive sampling, it's far off in terms of absolute values and in terms of tendencies, so that seems to be less useful. Now, however, so far, we calculate quality according to our quality model, which is based on a simplifying user model. So we actually wanted to verify whether those quality estimates correlate well with the quality as perceived by users. So we played different speech descriptions to users, and then we asked them to estimate the values for different fields in the query result, and then we judged them based on how close those estimates come to the actual values. And as we see here, those quality estimates according to our model correlate quite well with the actual prediction accuracy by real users. And we also did this for predicting relative tendencies in the query result. And again, the optimal and the holistically generated speech, they result in significantly better user performance than the speeches generated via sampling. Now, so far, we've only considered single queries, but data analysis is typically an interactive process. So in order to look into this, we performed another user study where we gave users access to a web interface for voice-based data analysis. And we asked them to perform exploratory data analysis on several data sets. One large data set about flight delays, which is often used for OLAP, by the way, and one small data set about start salaries. Now, we asked users to analyze those data sets and extract some interesting insights from them, and we gave them the choice between using our holistic voice generation method and another baseline that has been proposed recently. This is the interface that they saw. It gives them the choice between different voice generation methods for their queries. And first of all, we noticed that users were indeed able to extract non-trivial insights from the dataset via voice analysis. Here you see some examples where they connect, for instance, different dimensions, and they talk about quite specific data subsets. But more importantly, we asked users about their preferences between our voice generation method and the baseline. And it turns out that users, by large, prefer our voice generation method, and those tendencies are even stronger for the large data set, which makes sense because interleaving speech generation and speech output helps more if query processing is expensive, because then we save latency. So in summary, I presented a holistic approach to generating voice answers in voice-based OLAP-style data analysis, and we see that adopting this holistic perspective and specializing processing for voice output leads to significant improvements in terms of metrics such as latency, speech quality, listening comprehension by actual users, and user preferences. Thank you very much for your attention, and now I look forward to your questions.
What would you say is like the upper bound of complexity that that someone using data vocalization can infer?
Okay, that is a good question. So I would claim, I mean, that is actually interesting to have further experiments on that. I would claim that typically in data analysis, what we ultimately want to find out about the data are rather some high-level insights that are somewhat concise instead of single data points. So if voice interfaces work really well, I feel that they could give you those most important high-level tendencies directly, which you might otherwise infer yourself by looking at the visual representation of the query result. So I don't argue you can get more degree of detail from a visual interface, but in many scenarios, I would say that you might not even need that much detail.
Nice talk.
Thank you.
Did you set a maximum time limit? Did I get it right? There is a maximum time limit within which the voice output should be?
Yes, yeah. That is precise.
In that case, because sometimes what user remembers is not much of the time rather than how much key information is there. So if there's a little bit of rambling and then there's only one information, the brain can filter off those kind of stuff. Right, so did you measure by key information which the user...
Okay, that is a very good point, yes. So there's like several limits that users have when parsing a voice input. You also made some experiments on that, and you typically don't want to transmit much more than 3 facts. I was actually simplifying, so we have limits on speaking time, more precisely on the number of characters in the generated speech, which we use as a proxy for speaking time. But due to the structure of our speeches, we also have a limit on the number of facts that we transmit. So we essentially only transmit up to 3 facts to the user, and that is a number that they can handle, right? So I agree. You don't only should consider speaking time, but also other metrics, but we are doing that.
Okay, so the query template, the SQL query template you showed in the very beginning. Here I am. The
yes.
SQL query template you showed in the very beginning, that template would not generate the result, the right probability result that you've shown in all of your slides. It seems there was some pivoting or something going on, some self-speaking column and column and row names you've used there. Do you rely on some post-processing for the raw query output to make stuff more comprehensible in speech?
We don't really rely on post-processing, but we rely that the columns in the database have been assigned to names that are suitable for speech output.
Right.
Does this...
Well, let's take it offline. So I think the query template you showed would not generate this particular, would not show. Yeah, let's take it offline. That's fine.
That sounds like an interesting question, but I think this query template,
Yes.
okay,
would not deliver the result that you've shown like 2 slides later on or something. That's fine. So
that's result. So I mean, this description is a high-level summary of the detailed query result. All right, so this query result, I slightly changed the layout for better visual consumption. You're right that, of course, in reality, it would be a flat result. Agreed. But this is just for having a nicer slide.
Right. Thank you.
Sorry,